Okay. Okay, okay. Look, what have I done? Okay. Okay, so water is able to act like an acid and a base. I'm sorry, so back to your question, Jessica. So H plus, right, this guy, is basically acting like a group 1 metal cation, right? That's why hydrogen is placed, or that's one of the reasons anyways, why hydrogen is placed above the group 1 metals, right? Even though we know that it can behave like a non-metal, right? It also has these characteristics that are similar to being a metal, where it's pretty good at giving away its electron, right? It's pretty stable as an ion. So yeah, absolutely. So that gets back to this point that we were talking about before, where hydrogen's able to act like a nonmetal and a metal, right? Cool. So water is able to act like an acid and a base. Any molecule that's able to act like a base or an acid is called amphoteric, which is your $25 word for the day. Amphoteric. So a lot of biological molecules are amphoteric, meaning they can act like an acid or they can act like a base, right? They can be proton acceptors or they can be proton donors. So one more note before we move on from the auto ionization of water. What you guys are going to see, and it's really common, is that when we talk about H plus or proton, we use this interchangeably with the hydronium ion. The reason being is because the vast majority of acid-base chemistry happens in water, okay? So when you have a loose proton swimming around in water, it's not actually H plus, right? It's actually H3O plus, right? Because the water will hook up with it immediately. So that's why we use these two interchangeably, because most acid-base chemistry happens in an aqueous medium, aka we're in water. And if you're in an aqueous medium, that proton is not flying around by itself. It's hooked up with water as H3O plus, or the hydronium ion. Does that make sense, guys? So we use those two loosey-goosey interchangeably. Okay? Questions? We're cool. 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 All right. Can I erase? Awesome. Okay, so the next thing we want to talk about is acid-base reactions. Okay, and acid-base reactions are just another type of double D. Okay, so it's not really a new type of reaction, it's just an extension of the double Ds that we were talking about before. And you guys have already seen some of these, especially in the solutions chapter. We talk about acid-base chemistry a lot in the solutions chapter to kind of get you prepped for this one. So remember we had our base, sodium hydroxide. And our acid, hydrochloric acid. And just thinking about this as a double D, what products are we going to make?
Sodium chloride.
Yay! Aqueous or solid?
Solid?
Jessica?
She said solid. Can I just piggyback on that?
Do you want to?
No.
Cool.
Because I wanted to say aqueous.
Yeah, because aqueous is the right answer.
Ka-cha!
Yeah. So it's okay. It's okay, Alex. Okay.
I'm scared to jump.
No. It's okay. So, but this is one of the reminders that I wanted to get into with this example. So, remember when we talked about solubility, if something will dissolve or if it won't? We said that there are two basic rules to help you remember who will always be soluble, right? Who are they?
Sodium.
Specifically or more generally?
Group 1 metal.
Group 1 metals, right? So group 1 metal cations like sodium will always be soluble. Always, 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 right? No matter who they're hooked up with, that's going to be aqueous, right? What was the other example of something that we said is always going to be aqueous?
Nitrate?
Nitrates, right? So anybody that's hooked up with a counter ion nitrate will always be soluble. Everybody all right with that? Does that make sense, Alex? Yeah. So let's say we had something like this, right? Calcium nitrate is, it doesn't matter who's hooked up with nitrate. Anybody hooked up with nitrate is always going to be aqueous, aka soluble. Does that help, Alex? No worries. Any other questions about that? Cool. So, the last product that we have is H2O, which is a liquid, okay? So this is, I think, one of the first times that we've encountered a liquid in a chemical reaction. So, so there's a couple of important things that we need to know about a liquid. When we're doing the net ionic equation, guys, do we break down liquids? No, right, Katja? Yeah. So who's allowed to break down in our Ti and Ni?
Only aqueous.
Only aqueous, right? Only aqueous. Cool. We're going to break that rule today because there is one example of aqueous species that do not break down in our Ti and our Ni. I know, just to really f you guys up. So, and that's weak acids, okay? Can you guys think of a reason why weak acids wouldn't break down in a total ionic equation? Think about the name weak. What does that mean?
Because they don't dissociate completely.
Exactly, right? So if it's not breaking up into ions completely, then in the chemical reaction, we won't break it down. Exactly, Katja. Does that make sense? So if you can remember why weak acids don't break down, and if you can remember the strong 6, then you should be okay with that one, okay? I'm probably, and I probably shouldn't tell you guys this, but I'm not going to put something like that on a test because it's really hard to remember all of those acids, right? So I just want you guys to know that when you see that kind of reaction, if you see that the weak acid is not broken down, that's why. Because they're weak and they don't completely dissociate, right? So when we're doing a total ionic equation, we're assuming that things are able to completely dissociate, right? Sometimes that's a good assumption, sometimes it's not a very good assumption. So, cool. But everybody's comfortable with the fact that H2O as a liquid will never break apart in a total ionic equation or a net ionic equation. Cool? All right, so I just want to go ahead and do a real quick review of what each one of these guys represents in the reaction. So we have sodium hydroxide is the base, right? Hydrochloric acid, shocker, is our acid. And what we get on the product side, NaCl, is generally referred to as a salt. Now, this is kind of a bad example because you guys are like, yeah, duh, I know that sodium chloride is called salt. But this general term, salt, can be applied to anything that's produced in an acid-base reaction, right? And I'll give you some more examples of that, okay? So it doesn't have to be NaCl. It could be any counter ions that come together in an acid-base reaction, right? So you could imagine if this was, instead of sodium hydroxide, let's say we had potassium hydroxide, right? And let's say instead of HCl, we had nitric acid, right? What reaction would, or excuse me, what would be formed from this reaction? Potassium nitrate and
H2O.
and water, exactly, right? So both of these are salts. Does that make sense, guys? Yeah, I know. So when chemists talk about salts, they're literally talking about anything that has come together as a result of an acid-base reaction, okay? That's why we got to be careful with using that word around chemists because it means something much more broad than it does to a chef or any other person pretty much, right? So this would be another example of a base, and this would be another example of an acid, okay? And then, obviously, this guy is water, right? So, when an acid and a base react, we always form a salt and water, for the most part. Everybody okay with that? Cool. Now, I just want to take 1 minute to confuse the heck out of you guys. So I just told you that when an acid and a base react, you always make a salt and you always make water, right? However, if your base is not hydroxide, right, are you going to form water? No, exactly, right? So I just want to point out to you guys that this is the case only for an Arrhenius base, right? Arrhenius base being hydroxide, okay? If we're talking about a more generalized definition of a base, right, not all acid-base reactions will form water. Everybody still okay with me? Relative? Cool. So, I'm going to go through this pretty quickly, but I just want to mention one thing about the tie and the ni for this reaction, right? So, if we do the tie for this reaction, who are the spectators?
I have to write it out. I feel like I can't just look at it and know.
Let's do it.
It's me.
Oops. It's almost like I've done this before.
Almost.
Yeah, Kata. Sodium chloride. Exactly, right? So you guys see sodium ion over here. We'll cancel with the sodium ion over there. Chloride ion cancels with the other chloride ion, right? And our Ni, right, this is our tie, sorry, will just be this, right? So again, an acid reacts with a base hydroxide to form water. Okay? This is the most common net ionic equation that you'll see in acid-base reactions in general chemistry, right? This type of reaction is called a neutralization. Okay? The reason why it's called a neutralization is because acid makes things acidic, right? And a base makes things alkaline. We'll talk more about those definitions in just a second. When they react together to form water, water is neutral. It's not acidic, it's not basic. Well, technically it's both, but because it's both, it's neither. Does that make sense? Kind of weird, but yeah. So that's why we call this a neutralization reaction, right? When these two acids and bases react together to form water, they neutralize each other, okay? Questions about that, guys? We cool? All right. Can I erase? Cool. All right. So, we talk about an acid. What are the properties of acids, right? So this is a question that we want to know about, right? So why do we care about acids? Why are they so important? It must have to do with their properties, right? So a couple of very unimportant properties, more like trivia, are that acids taste sour, right? You guys already knew that. What kind of acidic drinks do you like?
Soda?
Soda pop. Yeah, soda pop. Penicillin?
Oh.
Is that
Oh.
is that a cocktail?
What?
Alex, I love having you lecture. I'm gonna miss you. How about lemonade? So I think everybody kind of knows that that lemonade is anything with lemons in it is going to be acidic, right? Yeah. I didn't mean to poo-poo your example, Alex. I just don't get it. Cool. So yeah, so we're familiar with this idea that that acids are sour. I think soda pop is kind of a surprising one. I think most people don't realize that soda pop is an acid because it doesn't really taste sour, right? Whiskey, lemon, yes, lemon, exactly. You're killing it. Thank you. That's great. We're all learning things today. Sounds delicious. Please have one for me. Everyone. Not drinking during a pandemic is bullshit, you guys. Sorry, I'm on camera. I should not be saying those words. Anyways, they'll be on the internet forever. Whatever. It's not worth it. If I don't know. No, I'm not going to espouse my feelings about drinking on something that's going to be on the internet for the rest of my life. But anyways, cool. So sour tasting, but yeah. So soda pops don't really taste sour, right? So I think the main reason why soda pops don't taste more sour is because the carbon dioxide kind of interrupts that that reaction in your palate. Have you guys ever tasted a soda that was really, really flat? It's kind of revolting, right?
Kind of gross.
Yeah, it's kind of gross. And if you think about it, it's probably because it's kind of acidic, right? So, yeah. So they taste sour. Can we eat all acids?
Absolutely not.
Absolutely not, right?
I'm trying to die.
So, if you had to guess which type of acid we're eating, right? Do you think it's a strong acid or a weak acid?
Weak.
Weak acid. Why?
Because and this is so dumb, but I feel like when I think about strong acids, I think about things that are like heavily aromatic, like something that smells really strong. You know what I mean? Like an acid. I don't know.
Okay. So the smell properties are a whole nother branch of chemistry, which is fascinating, which are called volatile organic compounds, or VOC for short. And those are all kinds of spectacularly interesting molecules. If you guys ever done like wine tasting or anything like that? You guys are probably not old enough to have wanted to taste alcohol things for fun. Alex has done wine tasting. Yes, Alex is old. Yeah. But there's a lot of tasting alcohols and foods is about the scent component, right? And that scent component is directly the result of VOCs that are produced a lot of the times by the cooking or the fermentation process, right? So it's a whole really interesting branch of chemistry, and some of them are acids and bases, but not generally speaking. So we can't eat all weak acids, but some of them can be eaten, right? Strong acids we never eat because they will kill us. So strong acids tend to be corrosive, right? What does that mean, corrosive?
They'll eat through things.
Yep, exactly that, right? They can eat through things. So whether or not an acid is strong or weak is of paramount importance to whether or not it can be useful biologically or whether or not it can be weaponized biologically, right? So a lot of diversity in the acid-base community. When we talk about the properties of bases, bases tend to be slippery to the touch. And I think that there's not too many things that are alkaline that we eat. So I don't know how strong the correlation between bases and flavor are in terms of taste. But I think a lot of alkaline flavors tend to be bitter, but that's not as generalizable as the sour thing. Most acids are sour. But yeah, cool. Slippery. Things like soap. Alkaline, right? Alkaline is just another way of saying basic, right? Basic meaning it's a base. Okay. Bases, I would say, are arguably less exciting than acids. Acids are more exciting, I think. That's where the action happens, right? The bases are kind of